Since my ray-traced image showing both the schematic and the integrated circuit mask layout of a NAND logic gate is the most popular image in my DeviantArt gallery, I decided to create a video explaining the electronics behind the circuit. In this video, I will describe the basics of the NAND logic gate designed using a CMOS gate array. I first modeled the integrated circuit mask layout for my ray tracer about 12 years ago, but created this newer scene a few years ago. The image in my DeviantArt gallery is actually a frame from my Project Glassworks video. A NAND logic gate outputs a 0 only when all the inputs are 1. The truth table and symbol are shown here. A NAND can be thought of as an AND with an inverter. An inverter is called a NOT. Therefore, a NAND is a NOT AND, thus the name NAND. I'll start by describing the schematic of the CMOS NAND logic circuit. For those not familiar with schematics, the symbols circled are transistors. Also, crossing or intersecting lines are only connected if there is a dot at the intersection, as shown here by the circled areas. In this application, transistors act as switches. The top two side-by-side transistors are p-channel metal oxide semiconductors. The transistor input is called the gate, and the other two legs are called source and drain. The direction of the arrows of the transistors show which type of transistor it is, PMOS or NMOS. And the legs with the arrows are the sources as opposed to the drains. PMOS transistors are normally on, meaning when the voltage on the transistor input is 0, voltage flows between the drain and the source. So as long as either A or B or both are off, which is 0, the output F receives VDD, or 1. The two bottom transistors are N-channel metal oxide semiconductors, which are normally off, meaning when the voltage on the transistor input is 0, voltage doesn't flow between the drain and the source. In this configuration, both A and B have to be on in order for F to be tied to ground, thus 0. And in this case, the top two transistors would be off, thus not providing VDD. Since both NMOS and PMOS transistors are used, the circuit is considered complementary metal oxide semiconductor, or CMOS for short. In case you need to review the combinations, here they are again. Now I'll describe the integrated circuit mask layout. Integrated circuits are created using a sequence of masks used for photolithography. For example, the basic mask sequence for an NMOS transistor is transistor area mask, polysilicon gate definition mask, contact area mask, and then metal definition mask. Thus, a mask layout represents the masks that would be used. CMOS, however, would require more masks. At any rate, the actual masks would have to be checked and modified to adhere to various spacing requirements. The blue areas are metal. The gray areas are cuts, which create possible contacts for the metal areas. The red areas are polysilicon, which form the gates. The green areas are heavily doped N+ or P+ diffusion regions, which form the sources and drains. The green area on the left are the NMOS transistors. Technically, the NMOS transistors have an understood or assumed P-type well diffusion, which would mean this design has an N substrate. This seems to be a little unusual, as most seem to have an N-type well diffusion on the PMOS transistors instead, and a P substrate. I didn't model the well diffusion distinction. Perhaps I should have. Here's what it might look like if I did. The new color was selected by me to be close to green, since I referred to green in this video. There doesn't seem to be a definite standard set of colors, especially since academic and industry switch the colors red and green. Back to the design now. A transistor is formed anywhere the red overlaps the green, thus polysilicon overlaps the fusion. The red lines conduct electricity from end to end. the left block creates the two bottom transistors in the schematic, and the right block creates the two top transistors. Therefore, the left metal strip is ground and the right metal strip is VDD. The two red lines with metal attached are the NAND gate inputs A and B. The metal on the far right attached to the green area through a cut is the output of the NAND gate. The squiggly metal in the middle connects the two sets of transistors together and to the output of the NAND gate. With this information, you should be able to see how the mask layout matches the schematic. In case it is still a little unclear, here's the schematic and the mask layout compared. The two side-by-side images show how the schematic matches the IC mask layout. For this discussion, G and D is ground, plus is VDD, F is the NAND gate output, A and B are the NAND gate inputs, and the colored rectangles surround the individual transistors, which are color-coded to match. Blank gate arrays are formed on the silicon wafer with the polysilicon, diffusion, cuts, and basic metal strips, which are not contacting anything, all formed in the first stages of the process. Then all a manufacturer has to do is make the metal connections needed to form the desired circuit. Kind of like writing to a blank CDR, but not as easy though. Each gate array chip may have several thousands of transistors, which is many more blocks than what I modeled. The modern incarnation of gate arrays is FPGA, or Field Programmable Gate Array. These are fully manufactured blank, so to speak, and are configured or programmed by the customer. No manufacturing required. They even can be reprogrammed. These really are like writing to a blank CDRW, and as easy as long as you know the coding language. By the way, I modeled another IC mask layout, an NMOS inverter. I won't bother describing that one, except to say the yellow area is a depletion implant, and the four metal lines at the bottom are inverter input, ground, inverter output, and VDD respectively. My university built an integrated circuit fabrication lab after I graduated from the computer engineering program. Had it been built earlier, maybe I could have made some of these circuits. They also created a supercomputer after I graduated, but the professor responsible for creating it was on my thesis committee when I pursued my master's in computer science, so I did get to see it during its construction. On another subject, I did design a simple 16-instruction microprocessor for a homework assignment. Maybe it could be made using a gate array. Of course, each one of those boxes contains many logic gates, so it's really more than it appears. This video only scratches the surface of the ever-changing world of integrated circuit design, as manufacturers constantly strive for ever-increasing circuit speeds and power.